Have you ever wished you could trap a single moment and replay it forever without pressing pause? Physicists may have found matter that does exactly that. It's called a time crystal, and it doesn't just sit in space, it pulses in time. Unlike ordinary crystals that repeat their pattern in three-dimensional space, time crystals repeat in the fourth dimension. They flip, wobble, or echo with perfect rhythm even when no energy is added. At first glance, that seems to violate the most basic laws of thermodynamics. How can anything move forever without using fuel? A Nobel laureate named Frank Wilczek asked that very question in 2012 and shocked the community. Many experts dismissed the idea as impossible or trivial. He proposed a new phase of matter that breaks time translation symmetry. The idea that physics looks the same a moment later as it does now. Yet curiosity is stubborn, and theorists soon discovered loopholes. The secret is many-body localization, a quantum traffic jam that keeps energy from diffusing. Imagine a city gridlock so perfect that cars oscillate in place instead of moving forward. Add a periodic push from a laser or microwave pulse, and the whole system locks into a dance that repeats every 2 beats. That dance is the first experimental signature of a discrete time crystal. Fast forward to 2021, when Google and NIST used a programmable quantum computer to create a time crystal with a string of 20 qubits. Their qubits flipped back and forth in double time for hundreds of cycles, far longer than decoherence should allow. Skeptics turned into believers, and the race to tame time began. In 2025, researchers at Innsbruck and Caltech reported a quasiperiodic time crystal that pulsed with 3 mutually irrational periods. That exotic beat could encode information with unheard-of stability. So what exactly is wobbling? Inside the lattice, spins of trapped ions or nitrogen vacancy centers rotate like tiny clocks. But instead of winding down, they trade energy in closed loops that never settle. From the outside, the material looks frozen. Inside, time itself is fractured into repeating shards. You might think perpetual motion machines are illegal, yet time crystals dodge the police by never doing useful work. They move, but they can't be harnessed to power a wheel. Their motion lives purely in quantum phase space, safe from entropy's grasp. To witness one, scientists chill ions to microkelvin temperatures and pin them with lasers. Then they strobe an electromagnetic field in perfect cadence. If the ions answer every second beat instead of every beat, a time crystal is born. Turn off the strobe and the dance stops. So causality is preserved, and no free energy appears. Still, the mere existence of the phase rewrites our textbook on what matter can do. Applications are already emerging. Time crystal oscillations can serve as qubits that remain coherent far longer than static spins. The University of Chinese Academy of Sciences used a time crystal phase to stabilize a superconducting qubit array. Meanwhile, Google's new Willow chip integrates tunable time crystal controls for error-corrected logical qubits. Because the rhythm never drifts, it behaves like an atomic clock that powers itself. That could unlock round-the-clock quantum sensors that never need recalibration, need to image neural currents or search for dark matter waves. A solid-state time crystal might hum quietly in your device, sampling magnetic whispers without draining a battery. Beyond engineering lies the big why. Why does the universe allow matter that flips forever? Some theorists see time crystals as thin windows into non-equilibrium phases. A catalogue we've barely begun to read. Others think they could bridge quantum thermodynamics and quantum gravity by revealing how time itself can fracture at the Planck scale. If you're amazed that a crystal can break spatial symmetry, prepare for symmetry breaking in space-time. And if that stirs your imagination, please like, subscribe, and drop your wildest time crystal idea in the comments below. Your question could fuel our next deep dive. So where do we go from here? Experimentalists aim to grow 3-dimensional time crystals that operate at room temperature. Optical tweezers already assemble thousands of neutral atoms into programmable arrays. By 2027, those arrays may host macroscopic time crystal layers you can literally touch. Philosophers wonder what happens if consciousness samples time through such oscillations. Could a brain-embedded crystal provide intrinsic clocking better than circadian genes? Neuroscience is quietly paying attention. Cosmologists also take note. Inflationary models suggest the early universe may have contained temporal domains that reheated in beats. If so, faint relics might linger in the gravitational wave background as rhythmic overtones. Detectors like LISA could someday resolve those cosmic heartbeats. A few contrarians even ask if time crystals imply that time itself is emergent, built from microscopic ticks. Perhaps past and future are stitched together by quantum phase transitions that never fully settle. That idea would turn arrow of time into spiral staircase of time. We don't yet know which metaphor will survive experiment, but we're finally equipped to test them. Will Google's Willow link time crystals directly into quantum error correction grammar? Will quasiperiodic pulses give us music of the spheres embedded in silicon? Will dark matter hunters discover new particles by tuning to silent beats of space? Every month the answers inch closer. For centuries, physics divided the world into solids, liquids, gases, and plasmas. The 20th century added superconductors, superfluids, and Bose-Einstein condensates. Now the 21st gives us matter that flows through time, the way water flows downhill. We are still learning to surf that temporal current. If you've made it this far, your curiosity already pulses like a hidden crystal. Hold on to that rhythm as we recap. Time translation symmetry can break just like spatial symmetry. Birthing oscillations without energy drain. Many body localization keeps the motion isolated from heat death. Periodic driving locks the phase into a clock division mode. Quantum hardware now fabricates and manipulates these phases with precision. Stability times grow by orders of magnitude each year. Potential applications include ultra-stable qubits, self-powered sensors, and perhaps new standards of timekeeping. What once felt like science fiction is turning into engineering design documents. But open questions loom. Do time crystals exist in nature, hidden in neutron star crusts? Can they form continuous rather than discrete temporal order? And crucially, how do they cope with noise in real-world devices? If they survive, quantum computers may hum to a beat older than silicon itself. Metrologists could redefine the second not by cesium atoms, but by condensed matter metronomes. Medical scanners might get silent, power-free MRI coils based on time crystal magnetometers. You might even wear a crystal-clocked fitness sensor that never needs charging. The path from lab curiosity to pocket gadget is shorter than it looks. All revolutions begin with a single strange observation that refuses to fade. In 1911, superconductivity baffled Kamerlingh Onnes. Today, you can buy superconducting magnets. In 2021, time crystal oscillations mocked our intuition. Tomorrow, they may steer our servers. As always, physics evolves by confronting paradox with experiment. Time crystals challenge our concept of equilibrium, but they obey every conservation law when viewed correctly. They don't cheat, they reveal loopholes in our oversimplified rules. And loopholes are where new technology hides. So the next time someone says you can't get something for nothing, remember the ions dancing in vacuum. They get nothing for nothing, yet they move and we learn. In their silent rhythm, we read a message. Nature is weirder and more generous than we dared to dream. Whether time crystals stay a niche quantum phase or reshape our infrastructure is up to us. The tools now exist. The imagination is the last barrier. When that barrier breaks, the future will keep better time than the past. Until then, every 5-second beat in this video marked 11 cycles of a real-world time crystal. Somewhere in a lab, ions flipped while we spoke. They will keep flipping long after the screen goes dark. Remember them the next time you glance at a wall clock that ticks and tocks and eventually stops. Beyond the wall, a quieter clock waits, one that never ticks out. Maybe we won't either if we ride its rhythm wisely. Thank you for sharing this pulse of curiosity. Stay curious, stay questioning, and keep time in your own hands. Because time, it seems, can crystallize,